I'm Seth Richardson.
I'm Mark Brennan.
I'm Roberto.
All right, and we're Team Cloudstat. So what we've made is a cloud-controlled thermostat that basically functions as a smart thermostat, very similar to a lot of the products that are on the market right now, but a lot more efficient and much lower price. So what we've done is we've created a thermostat that can basically be retrofitted into a consumer's home that is internet-enabled and talks to our servers that are hosted on the cloud. And what we send is information like the current temperature of the home. We also keep track of the consumer's set point temperature, which is what their desired temperature is. And then we also have another field called the set back temperature, which is a temperature that we can basically allow the home to go to save energy on heating and cooling. So the way our project works is essentially we send that information up, and we keep track of certain things like we said before, like the set back temperature, set point temperature, and the user's coordinates. And we expose that into an API that we've created. And our cloud will actually use that information to kind of determine what an ideal set back temperature would be for energy savings, depending on whether or not the user's in the home. And we've exposed that API. Both users and developers can use it. In order to kind of showcase that API, we've created an iOS application where we can kind of control some of this functionality. So I don't know if we can see this here or not, but on the application itself, we've got the current temperature and the set point temperature. We've just been kind of messing around with this, but what we can do is set this to a lower temperature here, like 70 degrees. And what we'll see on the front of the thermostat is that set point temperature is going to change to the temperature that we just set in a moment here. Actually, right now we've got it on an override, but change that to using the cloud there. So that just changed the 70 degree set point temperature that we wanted to have. Now, the way this works is as a user basically moves around, our set back temperature is going to either rise or fall depending on how far away they are from the home. So what we have is a user actually driving from Greenfield, Mass. We're kind of simulating the driving movement of that, driving towards us. So right now our set point temperature has fallen back to 66 degrees. The user's just basically driven into Deerfield, so that just changed from 66 to 68. And it's going to approach that 70 degree temperature in kind of a preheat mode. So that way, by the time the user gets to where the location is, it'll heat further. So now the user's in Sunderland, Mass, which is a little closer. That's going to go up to 69 degrees. And then we're going to have a few more points until they finally arrive at our destination here in Marcus. So now we're here, and our setback temperature is matching the set point. Okay. So this basically allows us to have more of an aggressive energy savings kind of schedule, as opposed to doing, machine learning and conservatively estimating where a user might be. We can actually tell with pretty good precision using the GPS coordinates. By scaling back the hardware and shifting the stuff to the cloud, we were able to take advantages of economies of scale. So we were able to get our unit costs down to $83 per unit, which is significantly less than Nest. We don't know what their margin is, but their cost is $250. So if you have a multi-zone system with, let's say, 4 zones, that would be a $1,000 implementation. For us, if you had 4 zones, it would be 4 times the 83 plus whatever we're charging. So if we're charging $100, it would be like a $400 implementation. So much more accurate, much less in cost, and we have an open API that the users can use.
Okay, great, thank you.